are going to continue on in 2019 AP Stat FRQ questions. We're going to do two today. These are relatively short, so I thought we could kind of run through number 2 and number 3. Number 2, I can only hope that you would get a question like this. This one is so easy. It's straight to the point, a little detailed, but I think you can really easily grasp these elements, right? So let's just jump right into that one. In number 2, it says a designing an experiment question. By the way, that typically is one of the lower scoring topics, so make sure that you pay attention to all the details that we're going to run through. In part A, it's going to talk about designing the treatments, the experimental units, and then what the response variable is. Okay, in order to get this correct, you had to identify all 4 treatments, which were pretty obvious, right? You had a 0 milliliter trial, you had 1.25, 2.5, and a 3.75 concentration of this fungus in sprays. And in order to get full credit for that kind of thing, you had to mention each one of those concentrations or the mixes or the sprays, however you wanted to talk about it. You had to talk about you couldn't just say the 4 sprays. You needed to identify each one, right? So, and you can see here, I listed them out and I said it was the different concentrations of sprays. I always want to write my answers in context of the problem. I don't ever want to write just a plain number unless I can't help it. So next part is experimental units. Be careful. It's not the insects that are the experimental units. What's getting the actual treatments? What are we putting these sprays into or on? And that was the 20 different containers of these insects. And so be careful when you're asking about experimental units. Think about your treatments. What am I going to be giving the treatment to? What am I going to be putting this treatment on or working with? In this case, you had 20 different containers that you were going to be putting these sprays on. And so that makes it more like an experimental unit. So it would be the 20 different containers of insects. In part 3, or the response variable, it was the number of insects that were going to be alive after 1 week. That was pretty self-explanatory. It kind of told you, what are we going to be counting? Once we're all done, once it's all finished, what are we going to be counting up? What are we going to be actually recording? That's the response variable. Okay, part B, does it have a control group? Well, is there a placebo, or is there a fake dose or a 0 level dose that they're going to be implementing? In that case, they would have a treatment or a control group. In this case, they do. They tell you that you have a 0 milliliter per liter, right? Which means that there is no spray. It's just water or whatever going into that container. Part C, to describe how to randomly assign treatments into these containers. And we've talked about this quite a bit, right? We had a number of things we had to actually list out. I'm going to create a way to equally, the probability of selecting them is all equal, and I'm going to create equal numbers of containers for each of the groups. And so I said, let's give everybody a number from 1 to 20, or 0, 1 to 20, that doesn't really matter. And I'm going to use a random number generator. You could talk about a die or putting names in a hat and drawing out the numbers if you want to. Any of those options would work. But you had to give each individual container a different number. You couldn't talk about, well, let's do, the same number for 2 different containers. No, that doesn't work. It has to be a different number for each one. Okay, so we're going to select 5 numbers, and the first 5 numbers we select without replacement. That's important. Either you say the numbers can't be repeated, or you say without replacement. We need to make sure that they're being selected independently, and they can't be selected more than once. Once we do that, we're going to select the first 5 to get the 0 milliliter. The next 5 are going to get the 1.25. The third 5 are going to get the 2.25, and the remaining 5 will get the 3.75 milliliter spray. As long as I did these 3 things, I would have gotten full credit for this piece. Number 1, I had to create labels for the units. In other words, I gave them a number from 1 to 20, or however you want to. You could have used letters technically, just so long as each one got a unique number or a unique name. You describe how to correctly implement the random assignment process. I said we're using a random number generator, and I'm going to allow each number to be used once and only once. It can't be repeated. That's how I said, without replacement. The third part was the random assignment process results in equal number of experimental units going to each treatment. We had 20 different containers. We had 4 treatments, so we had to get 5 sections or 5 containers to go for each of the different treatments. So long as you did that equally, that was the last component of that. And that's number 2. So that should have given you a 4 on number 2. I'm going to include the keys along with this. There was quite a variety of answers that they accepted on this one. And you could have done it in a lot of different ways, but so long as you satisfied those 3 key elements in your description, then you would have gotten full credit for that. Okay, we're going to move on to number 3. This was probability. This is probably not some of your favorite topics. However, I thought this one, for a probability question, this was kind of nice. They didn't try to trick you. They didn't go crazy with it. They went straight forward. They did twist a little bit and added a little bit of binomial distribution in here, but I think it was pretty self-explanatory how that worked out. And so we're going to kind of just walk through this real quick. You had a table here that was talking about the likelihood of someone taking medication as prescribed, whether it was never, sometimes, or always, and they divided that up into men versus women. The first part was really just about creating probabilities using a table. So this is just conditional or marginal probabilities, really just reading it out of the table and using some of my basic formulas like A and B, or A or B, or A given B, right? We all know those. Those are pretty straightforward. In fact, the majority of these things are actually listed on your formula sheet. So you could have just kind of pulled that up and kind of plugged into the formula and went there. Okay. 1, it said, the probability of being never and a woman in general, right? So I would have taken where those 2 values intersected, right? So never and the woman, I would have looked where they overlapped each other, and I would have said that number divided by the total in the entire table. This table is unique in the way that it had relative probabilities already set up. It didn't have the counts. So it didn't really matter. The number was actually there. I would have said 0.0636 divided by 1, which is obviously the same thing. And so that was the answer I had. As long as you wrote down that answer, that was fully correct. If you reported the correct probabilities, it's essentially correct for all the 3 pieces, right? So the next part would be the probability of being that was never, or you were a woman, right? And I wrote down the formula here: the probability of never plus the probability of woman minus the probability of never and woman. This is our general addition rule. You can look that up. It's 0.12 plus 0.53 minus the and part, which we did at the beginning. 0.5864 would be the correct answer there. In part 3, they ask you to do conditional probability. So I had to do the probability of the 2 things together, A and B, divided by the condition. In this case, it was never and woman, which we did that to start with. That was 0.0636. And then divided by the condition they're looking at, which is the probability of being a woman. And so in that case, we looked up there and it would have been 0.053. Divide those 2 and you get 0.12. So the probability that you never take it, given that you're a woman, is 12%. The last part, but the next piece here we have says that for the people in this survey, could we consider the events being a woman and never taking the medication as prescribed independent events? And we know that if the 2 things are equal, if the marginal equals the conditional, or if the probabilities are equal, then we can show it. And I wrote down a formula that we used. The probability of A, or never, equal the probability of A given B. If those 2 things are true, if they're equal, right, then we know that it didn't matter that you looked at a woman. 12% of everyone doesn't take medication ever as prescribed. And so in that instance, we found out that 0.12 is equal to 0.12. We can look up never from the probability up top, right? And it's 0.12 here. And never given this one is the one we just calculated, so we can pull that one down here. And if you describe this, because the probabilities are equal, then the events of being never and being a woman are definitely independent based on the fact that they're equal. The last piece here, it asks, assuming that in a large population, the probability they'll always take a medication is 0.54. That's from your table. If 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will always take medication as prescribed? Okay, and support your answer. 4 out of 5, that should be a real clear indication this is a binomial distribution, right? We have that binomial setting. We can say that it's one of 2 answers, a success or failure. Either they always take it or they don't, right? The probability of success in this case is always 0.54. That people taking medication, that's an independent event. If you take medication, it always doesn't affect me, right? And I have a specific number of trials. That's the part that's unique in this example. I have 5 people, and I want to do 4 out of 5. And so, actually, I wanted to do at least 4, right? So 4 or 4 and 5 different people. So I could have found the probabilities for each individual piece, and then do 4, then do 5, and I would have added them together. But we have a calculator that allows us to do this really quickly. And so you can see here, what's the probability that x is greater than or equal to 4? That's what I wanted to figure out. Well, let's define a few things. So you always have to do, if I'm going to use a calculator function, I need to define what the things are I'm going to plug in. For binomial CDF, that's where we're going, I have to be able to go, n is the number of people, x is the number of people always taking medication, and p is the probability of success. In this case, I define those, my n is 5 people total. I'm using p of 0.54, and I have x is greater than or equal to 4, right? And I went ahead here and I wrote out exactly what x represents in this problem. And then I wrote down the math that I used in the calculator to get the correct answer. So it'd be 1 minus the binomial CDF. It's minus because it's greater than. If I had less than some number, I would have just done CDF. But if it's greater than, that's when we have to do 1 minus one number less than the number I'm working with. So I did binomial CDF of 5, 0.54, and 3, because I wanted to get rid of 0, 1, 2, and 3. I wanted to leave behind the 4 and the 5. And that left me with 0.2415, which is the correct answer. To get this piece correct, I had to be able to do a few things. So part C, I had, number 1, I had to indicate that it was a binomial distribution, and I did that by using binomial CDF. Number 2, I had to identify what n was and what p was, right? And I did those, I listed those right here. N is equal to 5 and p is equal to 0.54. I can't do it here. I'm using those numbers, and I know that's true, but they're not going to accept you just punching in a calculator and saying this is what I typed in. They want you to define that out. At least I don't think they would give you credit for that. Okay. 2, I had to indicate the correct boundary and the direction of the event. And I did that right here. I said that I wanted to find out the probability that x was greater than or equal to 4, right? So when I did that, I told it I wanted to be a greater than direction, and the boundary was a value of 4. I don't think you could have done it with the 3 here. I don't think they would have accepted that. And the last part is obviously you had to get the correct probability at the end of the equation. Okay? And then that would have been it, right? If you would have done each of these 3 things together, that would have given you a 4. I'll post the key, so if you didn't get them all correct, you can kind of adjust it to your own liking. There's too many options for me to go over here. But that concludes the second and third equations or problems on the 2019 exam. Okay, I'll finish up the next few, so keep checking back.